Hi, good evening, everyone. My name's Stephen Peat and I'm the Chair for Home Counties South East. And just before I introduce our presenter this evening, I have a couple of announcements to make. First of all, thank you for taking the time out to attend this evening, and thanks to Ella from Regions Executive at Balham providing all the much needed technical support for this meeting to go ahead. And just really a reminder that as Ella lets you into the meeting, that CIBSE regions are in place really to support the charitable objectives of the institution and encourage the intellectual welfare of members and improve the understanding of building services engineering among a variety of other professions and society in general. And this is carried out by organising periodic meetings and other activities related to the theme of the built environment. So, if you have future ideas for meetings or other activities, please email me and I'll leave my email address. We also have tonight as well, after the main presentation, after the technical presentation, Emma Linnane, and she's Senior Membership Development Executive, who's going to provide some pointers where members can go to follow up about the membership application process, moving through to other membership grades as well. So if anyone is looking at corporate membership and or professional development, this short presentation, which Emma will give, will be about 15 minutes, and we'll go over the main routes into membership as well as cover academic requirements, the application process, as well as the interview. And there'll be time for questions after the presentation. So just a couple of housekeeping points. If you could have your cameras turned off and your audio on mute, this will help with transmission. And if you have questions, please put them in the chat box. And at the end of the presentation, I'll read the questions to the speaker and ask the speaker to respond. So thank you for that, and I'd like to introduce you to Ken Neal from Solid Energy, and Ken's presentation is on heat pump technology and heat networks for commercial buildings. So thank you, Ken, over to you.
Good evening, everybody. I'll just introduce myself and give you a bit of my background. I've been in the fossil fuel sector for most of my life, maintenance of large oil and gas boilers, and for the last 3 years I've been working for Solid Energy. So in some ways I am probably got the same experience that many of you will have had, which means that there isn't a great deal of extensive heat pump experience, but I've spent 3 years working for them, been over to Denmark before COVID, and my role was to introduce their heat pump technology into the UK and begin to speak to consultants about the products that are available. I'll just move over to my screen and bring the presentation up. So the agenda is round about carbon reduction, climate change, where we are. Probably flick through that because we're after last week with the COP26, we're probably up to speed on that. But just an overview of heat pumps, ground and water source. I'll go through the air source, which we happen to specialise in, the comparisons between the different heat pumps, some technical, some design issues, recent legislation, some of the incentives that are available, and the issues of commercial returns. And then lastly, at the end, I'll answer any questions that you have. The primary focus has got to be on the understanding of heat pumps and their applications. I won't read through that slide, but we're in a position now where we've got to reduce our carbon footprint. We've got to clean up the air of cities. One of the only technologies we can go to now is heat pumps. Yes, we can wait for hydrogen and perhaps potentially other technologies, but at the moment, if we want to go for net zero carbon with local low emissions, then it's heat pump is the technology that we are using. Just to go back to basics, the ultimate renewable energy source, of course, is the sun. We're capturing that energy, whether it be through the warm water or warmer water that percolates through the ground, that has captured some of the sun's energy, or indeed whether we are capturing the sun's energy in the air that we have around us. We've got to get back to that. We've got to remove ourselves from fossil fuels. Carbon reduction, we've got to have a policy that's affordable, and that's a whole presentation could be taken on that. The spark gap between the cost of gas and electric is very, very difficult to defend at the moment. Resilience, we've got to make sure that there are alternatives, forms of energy available, and then of course we've got carbon reduction, and at the moment, as I was saying, we've only got the heat pump technology to go with that. Why act now? Well, I think we're at a stage, we've all read the newspapers the last few days. We are now at a time to stop irreversible damage. Current building regulations now are beginning to identify the problems and to force us away from fossil fuel dependency. Public awareness is shifting rapidly. I think a lot of universities are finding now, for example, that the students are demanding that the campuses are decarbonised. Generational pressure. The young people want answers. They want a secure environment to live in. We've got the Greta and Attenborough effect. Every time you turn the television on, we have news of climate change devastation somewhere. We have got the technologies now that are tried and tested, although they're not here in the UK in the numbers that they are in Scandinavia. For example, 65% of properties in Denmark are on district energy, and heat pumps are the go-to technology for district energy centres. So although it's not here, we can bring that technology over. It is tried and tested, and we can begin to modify it as we must and introduce it into the UK. We've also got the rapid development of the electric vehicle market, and we've got to hope that the national grid can cope with the pressures that heat pumps and electric vehicles will play on the systems. I guess you've all seen those graphs before. The decarbonisation of the grid, the carbon levels now are a fraction of what they were, and going forward past 2032, they're only heading in one direction. We were up a few years ago at 500 grams per kilowatt of electricity. Now we're right down into the tens, occasionally get as low as 80, but certainly averaging between 100 and 200. This is an indication of a sample of the national grid. One particular day recently, 85 grams CO2 per kilowatt hour, predominantly, of course, wind and solar, nuclear, gas, biomass, lower down the table, no coal showing at all. Of course, we are still weather dependent. We have to remember that the gas will be with us for some time. We can't depend upon certainly wind and solar. And although there's some good news about smaller nuclear plants, that's going to take some time. But what we can do is we can capture the low carbon electricity that is available. We can use that with good COPs on heat pumps and turn that into very good and clean thermal energy. If we continue that vein, if we look at the black square there, we've got coal generating 630 grams per kilowatt hour delivered heat, going down oil, gas, direct electric heating, which of course is 100%. But then if you look at ground source, we've got 320% if we have a COP of 3.2, or indeed 400% if we get to 4, which is perfectly possible, especially on ground source. What has held deployment back? Well, when you look at those two tables there, if you look at gas, we've got the most expensive gas in Europe. Sorry, the cheapest gas in Europe, because of various subsidies, and with the tariffs that are thrown onto our electricity bills, bizarrely to encourage renewable energy, some of them, then we've got the most expensive electricity costs in Europe, and that gap is making it hugely difficult to suggest that heat pumps have a buyback period. You know, most people want to invest in new equipment to save funds going forward. At the moment, I have to confess that the large heat pumps are only being sold to people who want to decarbonise and to be blunt, can afford the capital cost and the increased running cost, and that's not a good place to be. I really do hope that over the next months and years there will be a change of government tack here. We can reduce the gap so that we are not fighting against the high electrical costs. We do have various ways we can put up some defence against costs. We can use thermal storage, which I'll talk about later, and that is to ensure that we can capture electrical tariffs overnight in thermal storage, and also we're just moving on to demand side controls, when we can install controls that allow the heat pumps to be switched on and off during the times that are convenient for the national grid. So if there's a lot of wind energy and they don't know what to do with it, they can dump it into heat pumps. The larger ones, especially and they actually pay for the privilege of disposing of their excessive electric capacity in order to keep the local grid balanced. What is changing to make heat pumps a technology now? Well, we've already talked about Part L. We can ensure that Part L is used now as a route towards heat pump deployment. We've got the adoption of innovative district heating solutions, co-location of seasonal heating and cooling loads, where we can actually think about using the ground to both store heat and as a store for heating loads in the winter. New thermal storage technologies using phase change technology can be effective as battery storage. Advanced size management, which I've just mentioned. Progressive deployment of design and deployment standards. That's really about making sure that we are designing new installations to suit heat pumps, moving away from the conventional 82-71 flow and return temperatures, moving towards potentially a 60-40, 65-45 is ideal as well. And for that, I think we've got to get over to the consultants and designers what heat pumps can and cannot do. And we've also got the public attitude to emissions, where we have the benefit that on-site heat pumps do not throw out any emissions into the local atmosphere. And when you're talking about, a 5 megawatt or even 10 megawatt heat generation in the middle of a city, that has got a lot to say for it. Onto heat pumps. I'll just flick through that, but this is the simplest level. It's a box which uses electricity to move heat. You will all got a heat pump at home. It's a refrigerator. It's moving heat from the fridge, from the items in the fridge into your kitchen, and it uses exactly the same process. It's only got an evaporator, compressor, condenser, and a valve to control the flow of the refrigerant around the circuit. The electricity that is consumed by a heat pump is to move the refrigerant around. None of the electricity that goes into the heat pump comes out as thermal energy. It is to it's to provide the refrigerant with that heartbeat to move around. It absorbs the heat, it vaporizes, it is then compressed, and when you compress it, it increases in temperature dramatically, and then through the condenser that heat is released. It converts back into a liquid and then goes through a control valve to start the process again back into the evaporator. I'll flick through these. This is a domestic ground source heat pump. This is just to give you some idea of what it looks like. Remember, we've got to have a water collector system outside, whether that be open water or groundwater through trenches, which I'll come on to, or boreholes, which I'll mention as well. Conventionally, they are considered to be better with underfloor heating or large heat emitters. That very often supported with immersions to generate domestic hot water. Commercial, which is the size that Solid Energy would be doing, very much similar to the small domestic heat pumps, just with everything on a larger scale. We can heat and cool, and as ever, the control systems are key to this, monitoring the temperatures, monitoring the pressures, controlling the valves, and making sure that the heat pump is running as effectively as possible. On the ground source heat pumps, we've got to understand that the important aspect of this is the drilling and the geology. Ground Source Heat Pump Association is a place to go for this. British Drilling Association. Drilling standards are being rewritten. They have to be. They do have to be rigorously enforced. The quality of the water collection cannot be understated, and there are unfortunately some examples of inadequate water collectors installed by people who are not following the standards. Open loop, they're taken from lakes, canals and rivers. We've got to remember that we don't particularly want the source water to go through the heat pumps. We would prefer place exchanges in between. So if there is any cleaning to be done of any biological growth, that can happen within the place exchanges and not the heat pump. Boreholes, drilled boreholes, UK average coming out to around 11 degrees C. Non-consumptive, the water can go back in, so we're not using the water resource, we're just using the energy out of it. But we have to make sure, of course, that we are putting the water back into the ground a distance away from the supply. So we can't suggest that boreholes are going to be very easily installed everywhere, and we need the right ground surface. We need the buildings to have the ability to have boreholes at a distance. Closed loop, where we put a heat exchanger out into a sea, a river or canal. The main concerns is how to anchor it down, and also, of course, how to maintain it. So it's got its advantages. It's got its disadvantages though when it comes to maintenance. Ground loops, much more conventional now, where we are putting loops down boreholes, pumping water down into the ground, chilled from the heat pump, allowing that to be warmed up and coming back to the heat pump as an energy source. Closed loop horizontal, plenty of land needed here, trenches a metre wide, largely depending upon, again, on the local geology. This is harvesting still solar energy. The heat replacement will be through rainwater, which is surprising. Boreholes do have an element of geothermal energy in them, but here we're capturing solar energy in the form of rainwater percolating through the ground. So there's a vertical drill closed loop, conventionally 150 mil, 5 to 50 millimeter sensors, and we go down to what it says here, a maximum of 300, conventionally more like 150 to 200 meters. Again, depending on the geology, and one of the disadvantages of ground source is that there is a need for a report, a feasibility study to be carried out, and of course those are expensive, and at a commercial level very expensive, and they may in fact only go to prove that groundwater isn't feasible. District options, we've got now 4th and 5th generation, where we can have one main heat pump supplying numerous properties, or alternatively shared loop in the ground serving heat pumps within each individual premises. On the planning side, this is really the stick bit of heat pump deployment. The GLA back in 2019 invoked a recommendation from BASE. BASE were wanting to give this a bit of thinking time, but the GLA came in and said no, from now on we're going to use the new SAP regulations. We're going to encourage the use of heat pumps, and we don't want any more gas CHP in the boundaries of the GLA. Sadiq Khan, he said that in the early 50s they closed the power stations, Battersea, etc., to clean the air, and ever since then we've been putting in mini power stations, which largely defeated the object. So the GLA guidance was interpreted by the planners more as a regulation than guidance. So London has been the centre of interest with heat pumps. A lot of projects that I've been involved with have been in London, and over time, of course, using the Merton rule, what London does, the rest of the country will follow. This is talking about capturing overnight tariffs. One company happens to be Octopus. They're using agile tariffs to encourage all heat pump users to build up thermal loads during the evening, overnight, when the electricity supply is cheaper, so that the heat store then can dissipate the heat during times of expensive expensive electricity costs. That one can be dispensed with. Bit of history now, unfortunately, but the renewable heat incentive was a bit of a disaster when it came to heat pumps. Generally, went on to biomass, and I think an opportunity was lost with regard to using it for heat pump deployment. On ground source, when you are looking at contemplating ground source heat pumps, there is a lot of agency regulation. I was speaking to one guy from the EA last month, and he unapologetically was telling me that they're overloaded. There's not a lot they can do about it, and it's going to be 6 months before they can promise to do much about it. So there we are. The AE are interested, of course, in making sure that they do look after the water courses, and rightly so. But there seems to be a reluctance to actually resource themselves sufficiently to deliver a good service. Standards on ground source. We've got a number of guidance documents there, including, of course, your own CIBSE library. And then just to go on to air source heat pumps. Why air source? Well, to state the obvious, it's always there. There's no problems about access to it. There's no tax, duties or fees yet. It's non-polluting. They can produce good COPs, and the installation costs are much more predictable than ground source. There's no reports needed. There's no geologists needed on site. There's no licensing from the EA. So there's a lot of good points, but, and there's always buts, we need a large footprint for evaporators, especially at commercial level. We've got to worry about noise. We've got to worry about cold air plumage. Where does all that cold air go after we've abstracted the energy from it? Defrosting. We've got to worry about chilling air at 5 degrees. We'll chill it down to freezing. So we've got to know what can we do about that. The RHI funding, I'm sorry, is a dead item now. That's history. But lastly, we've got the seasonal fluctuations in air temperature. Unlike water, which is a relatively constant source of energy for the ground source heat pumps, with air, of course, we can go from -4 to +20, and the heat pumps have got to be able to deal with that. That's what a domestic heat pump looks like. Just for those of you who haven't seen it, sitting outside a property. That's our heat pump. That's a Ringkøbing reference site in Denmark. 3.2 megawatt. You can think of the area that those evaporators use as a tennis court. So it's very heavy on land usage, unfortunately. If you are underneath those evaporators in the summer, it is a very pleasant chill. If, however, you are underneath there in the winter, it is mighty cold. So we've got to worry about where the cold air goes. You'll notice that the location is quite a long way from residential accommodation. That is because the noise issues. So when we want to put these in the middle of London, we've got a few problems to contend with. That's what the 5 megawatt air source heat pump looks like. We can think about 2 tennis courts plus the building with the compressors in. So again, we're talking a lot of land. That is what a 250 kilowatt solid energy heat pump looks like. 2 compressors. That is twin stage. That would be able to raise water temperature up to 90 degrees. If it was just one compressor, we'd be going up to 65 degrees. Some of the comparisons, the advantages and disadvantages. Air source, we've got predictable costs, but we've got the problems of space, noise, cold air, lower funding there was. Ground source, we had better RHI. Ground source generally quieter. We've got no fan noise. Generally increased seasonal COP, but we've got the ground survey costs and also the unpredictable civil costs. We can flick on from that one, but that's just to show you that, I suppose, the difference in ground. Before our RHI was closed down, people were getting 9 pence for ground source and only 2.75 for air source. The efficiencies of heat pumps in comparison, this is very general, but ground source, because the controls and because the heat pump can be designed specifically for a constant temperature throughout the year, especially on deep water. Okay, rivers might change a little bit, but no water changes in temperature as much as air across the seasons. So that's a rough guide, but just to indicate that air and water can not generally obtain the COP ratings of ground source. Some of the legislation in 2019 was a good year. All those documents are available. This is an interesting slide. Family house in Denmark, in Scandinavia. They reckon that with a large delta T on the heating system, the fuel consumption is so much lower, and they've done that Fisher-Price style, showing a nice large tanker delivering a fuel to a building with a delta T of 10, as opposed to a nice little mini tanker to a delta T of 40. Interesting that that's one slide from Scandinavia, which always amuses me when we've historically been using 82, 71 operating temperatures in the UK. I think we've been through that slide. That's the old regime where the heat pump was down as seen by the planners as a poor alternative to gas CHP, and that is the new regime under SAP 12. The economic potential, some of these are achievable in certain circumstances. I would suggest that heating cost reduction by 30% is unusual. It can be done. It's got a bit of salesman's talk about it, I'm afraid, but if you're on oil and you've got really good opportunities for ground source, you may be able to do that. I think the line there that I'd like to talk about is the integration with other heat sources. I think that if a commercial building especially has got a fully functioning fossil fuel system in, then rather than contemplate taking it out, a really good alternative is a bivalent system. Put a heat pump in, allow it to do up to 90% of the load, can reduce the carbon footprint by 90%, but that's probably at half the price of ripping out the gas and going for 100% heat pump solution. If you want to go into the technical details of sizing a heat pump, I can let you have a calculator which helps put the flow and return in, the heat demand, and it will give you numbers as to what heat pump you actually require. On the graph on the right, the blue section is actually the heat demand that is not covered by a heat pump. That's a bivalent system, whereby the green is the heat pump input and the blue would be the existing gas or oil boilers. We've got a calculator which shows the green line across the graph on the left is the electrical input. The red line is the heat output. The black line is, of course, the heat demand from the building, which is falling dramatically from -10 to +18, as you would expect. The blue line is the COP for this air source heat pump. So at -10, the COP is only at 2, and at +18 is at 3.2. That kink in the middle, that steep decline, is actually due to the defrosting cycle, and that is where we have to use some energy to defrost some of the evaporators, but we do it in a cyclical fashion, and the actual output of the heat pump should not be too adversely affected. But for air source heat pumps, there is a defrost cycle, and that does impact on the overall efficiencies. This is just another graph to show you that if we design a heat pump to deliver 1,500 kilowatt, that's surrounded by the red line, we can actually deliver just under 90% of the load. And if we do that, rather than supply a 2 megawatt unit, we are reducing the capital cost significantly, and we're allowing the gas boiler to do what it's there for, to top it up, and of course also to provide some resilience. Another diagram, this time showing heat pumps working with other energy sources for peak load cover. Here we've got a gas CHP and a thermal store, and a water source heat pump, again probably providing certainly more than 50% of the energy demand. Just going forward, this is my last slide. This is called a vacuum ice maker. This is where we use far less water. We actually freeze it. We abstract all the energy out of the water, and we produce very efficient hot water and ice. Unfortunately, we then have to dispose of the ice in the form of slush, so we've got to pump that back into a river with environmental consequences. So what we're hoping for on this one is to find a use for the ice and a use for the heat, all in the same place. So that's the heat pump of the future. A slide here, great comparisons between the maintenance costs of heat pumps. Very last aspect really of the benefits, but when you compare heat pumps to other technologies, CHP and biomass boilers, it's a bit like the statement, when last did we get our refrigerators serviced. There's no combustion, there's no dirt, there's no issues around maintenance regimes determining the life cycle of heat pumps. Heat pumps are designed for 100,000 hours, basically with no oil change. So we've got a maintenance-free product compared to the other technologies we're used to. I'm sure this presentation will be available. Actually, there are a couple of other slides on challenges, which I suppose we need to just mention. They are not only suitable for new buildings, they don't lose all efficiency in the cold months. So it's hard truths which have been turned into fact, really. And there's some opportunities of and benefits of heat pump deployment, and that's the information that anybody would need for a basic feasibility study on whether a heat pump is suitable. Here we are. I hope I haven't gone too fast or too slow, or I hope it's been appropriate. I will stop sharing my screen and hope.
Hi, Ken.
I hope that was about right, Stephen, for you.
Yeah, that was excellent. There's some there's quite a few questions in the chat box, so I think we'll move on to them. But yeah, thank you. Very informative and really updated my knowledge. So yeah, thank you. Excellent presentation. And some of the people couldn't access the chat box, so they've emailed me, and the first two questions really merge into one. What are the factors in a heat pump system that improve COP, and what ways to increase the efficiency, coefficient of performance of a heat pump system?
That is an excellent question, and I really should have included that. Heat pumps efficiency is determined very much on the operating temperatures that you expect out of it. I think I only glanced over that, but if we have a heat pump that's running at 65, 45, we can expect a COP of between 3 and 3.5. If the operating temperature is 85, 65, we can expect a COP of less than 2.5, and the running cost over the lifetime of the heat pump is huge. So it is much better to invest on new build, get the right HIUs in place, stick to 65 degrees. If we can produce 65 degrees, deliver 60 to the HIU, that's more than adequate enough now for domestic hot water. On retrofit, we need to think about either using a bivalent system where we've got gas boilers to top up the operating temperatures, or we need to consider removing bypasses, bringing down the flow and return temperatures. And I think we will find that actually 85 is not essential in some buildings. We can over time bring that down so that it's more in line with what a heat pump needs to generate good COPs.
And there seems to be a myth about heat pumps operating at small delta T's. You mentioned quite substantial delta T's there.
Yeah.
What are the factors there that affect that?
Well, when I've been talking to consultants, I've been saying that we use propane and we use isobutane. Isobutane is the refrigerant that's in 85% of domestic fridges. So I'm talking about the characteristics of hydrocarbon heat pumps. And we want large delta T's. We want delta T's that are over 10. If the delta T is 40, great. Now, there are other manufacturers, and they've got their place in the market too, but they are using different refrigerants, and they will bore at an increase of 10 degrees for a delta T. So it's horses for courses. What should not be stated generally is that heat pumps do not like large delta T's. That is factually incorrect. Some heat pumps love large delta T's. Other heat pumps can't cope with large delta T's.
Brilliant. Thanks for that, Ken. Question from Demetrius, a bit of a statement. It said, in SAP 10.1, October 2019, a grid carbon factor for electricity is 0.136. Is that right?
Yeah, I think it is right.
Yeah. I've actually got some responses a bit later on to that. We might come back to that in a minute. I've got a question from Rosella. You were talking about running the air source heat pump overnight to charge the thermal stores. But in this period, although the cost of electricity is cheaper, the COP is worse. Did you carry out any studies about pros and cons in this?
The COP on the ground source would not be any worse because that. And we have looked at the difference in air temperature overnight. We still believe that the principle of capturing cheap electricity overnight is very much worth it. You know, we have some consultants have looked at that. They've still come back, and what they're saying is that the additional cost of the increased thermal store over a 20-year period will well be affordable.
Brilliant.
And we've got to remember that demand side control, which we don't know a lot about, is coming on the scene, and for that we do need large thermal stores.
Yeah, and another sub question to that. Also, do you have any guidance about cold air plumage and stroke microclimates? Yeah.
Significant research has been done, especially in London now. There's a specialist, Joel Gustafsson. He's got all the modelling. He's taken on a lot of the modelling from many of the consultancies in London. It does have to be considered. We're taking 5 degrees out of the air, and there's if we're putting a 5 megawatt heat pump in, that is a lot of cold air. Where does it go to? What we want is the unit as high as possible to allow as much wind to take that cold air away. The nearer the ground, the greater the importance of the modelling, but it does have to be considered. Cold air plumage and noise are really the two biggest considerations for putting air source heat pumps into urban environments.
Just a comment from Chris we're on SAP 10.2 now, and the grid factor in SAP varies monthly. 163 grams per kilowatt hour in December and 111 grams per kilowatt hour in July, for instance, for imported electricity.
Right, good point.
Another question from Rosella. It'd be interesting to receive the calculator. So if you can send that over, Ken, I can make sure that gets sent out to everyone who's on the on the presentation.
Yeah. I'll send you our AWC calculator. That's for air to water, and then could everyone please bear in mind that it's a feasibility study tool. It's basic information. It's something that you can come back to us with suggestions of a heat pump. We will then double check it and confirm that everything's right. So it's really a user-friendly tool for designers to do the first stages of a design.
Yeah. Comment from Chris, SAP 10.2 will give a different factor for gas CHP for exported electricity. So he's suggesting that you might have a look at your numbers, and there's SAP 10.2 updates for heat networks, publishing.service.gov.uk. I
have to confess, I should have updated a few slides in that presentation. Guilty of all charges. Of course, I think it's evidence of the heat pump world being very busy, Stephen. So I will update it. The principle, however, is that the SAP is now encouraging heat pump deployment and discouraging CHP. I think the numbers still would support that. Yeah,
plenty more attendees would like your calculator. So yeah.
Right. Okay. Yeah.
Why do you think what you showed that second to last slide is the heat pump of the future? Why do you say that? That's a question from Rosella.
It abstracts the same amount of energy from water using 10% of the volume. So it's super efficient because we can dramatically cut down on the parasitic electrical load of the pumps. It's just really to demonstrate that heat pump technology is not static. It's a long way from deployment. It's really at concept stage still in Denmark, but it's just to indicate that heat pumps are moving on. I would suspect that in 5 years we will have an ice making heat pump, as bizarre as that sounds. So it was just a little novelty slide. Nothing. Please don't be ordering one at the moment.
Yeah, that was one of the next questions actually. When will it be available? You think about 5 years from?
Well, it's one of these things which I think we're getting some partners on board in the UK who want to run with us on that. We're busy in Denmark making heat pumps as fast as we can, and sometimes we need the extra resources of a R&D partner to take that on board. But that could happen, and it could be quicker. But at the moment, it's a little bit pie in the sky.
A question from Phil, and I think you've partly answered this. What refrigerants do heat pumps use?
Well, if you go on to Google heat pump refrigerants, I think you'll find approximately 1,000. The main ones are ammonia, which historically has got a good history, not, I would suggest, for use in a residential environment, can have slightly higher COP levels than hydrocarbon. We've gone for hydrocarbon, propane and isobutane. Then you move on to the artificial refrigerants, HFCs, HFOs, which are, for one reason or another, being reduced. Predominantly, of course, because of global warming potential. Ammonia, global warming potential is 0. Propane is 3. And I think some of the artificial refrigerants have a global warming potential of 1,600. So you can see the comparison. Propane is not as good as ammonia, however, it is light years away from the artificial refrigerants.
Yeah. A question from Montesino. Heat pumps are very good, no doubt, but they are not maintenance free. Could you talk a little bit about maintenance of them, things like cleaning coils and gas charge leaks?
Well, you've got me on my strong point then. I've spent years servicing and maintaining boilers, CHP, biomass boilers, and although maintenance free is obviously an exaggeration, I was drafting out a maintenance schedule, and it's about checking refrigerant levels, it is checking safety valves, it is about cleaning any leaves away from the evaporators, and I jokingly put at the bottom, and we'll take some polish and we'll polish the compressor just to show we've been on site, because there is very little to do. Now I'm talking about hydrocarbon refrigerant. If you go to ammonia, that's a different matter altogether. You've got piston compressors with oil changes, and if you miss an oil change, you'll seize a compressor. So I am specifically talking about our solid energy heat pumps. So I hope I haven't made that a general point, but it's another reason why we've gone for hydrocarbon as opposed to ammonia.
Brilliant. And of course, is there the experience in the UK in that area to maintain these products? Is that
well, just as yes, there is, because it's a refrigeration cycle. Solid Energy have teamed up with Clade. Clade manufactures CO2 heat pumps in the UK, but they also look after the refrigeration plants for Waitrose, Aldi, Tesco. So we are using their workforce for technical support in the UK. So the average gas burner engineer, no, he's got to be retrained, but refrigeration guys, it's second nature to them.
Right, brilliant. Question from Phil: what external temperatures are you using when you quote your COP figures? COP
is a calculation that's based upon a European standard. It's nothing that we compose. They use a guideline. I think it's -7, -2, +2, and +12, which is the numbers that we use. But that is governed by a European standard. The one good thing about an SCOP is you can compare a solid energy heat pump with a Mitsubishi heat pump, with a Star refrigeration heat pump. It is not a number that we can come up with ourselves. I will add to that, however, that solid energy do include defrost in that calculation. I don't believe you have to. I believe other manufacturers take away the defrost energy losses. So if we want to compare ourselves with them, we actually add 5% onto our COP number, which turns 2.8 into 2.9, but to keep the playing field level.
A question from Adam: in regards to retrofitting in a current single glazed commercial property with a gas boiler, wet heating system, is the best way of retrofitting a heat pump to maintain the current gas boiler and install heat pump with an immersion heater to offset carbon emissions and improve efficiency?
The best way is to go down that bivalent route, heat pump in to provide the base loads, probably for the domestic hot water as well, if needed. Leave the gas in just to top up, and you can reduce the carbon footprint by up to 90%.
Great. Comment from Nancy: I agree, refrigerant circuits, especially on large systems, should be carefully checked regularly by fully qualified F-gas registered engineer.
Yes.
Question from A Toppin. Typically, air source heat pump operates with a narrow delta T. How do you address the secondary side of the circuit, which may have a wider delta T due to simultaneous heating and domestic hot water loads?
I think the first line of that is we can challenge. We don't want no delta T. We can deal with 30 degrees delta T. We you know, it's not a question of coping with it. We encourage it. It increases the COP.
Yeah. Great. Question from Matthew. Would an scope, which is seasonal COP, be a more relevant figure to use rather than instantaneous COP?
Yeah, you know, in any measurement of efficiency, you have to look upon it at 12 months. You know, I can say under certain circumstances, we can get a COP of 4.5. But if that's only when it's 18 degrees out and the sun's shining, that is mis-selling and taken to its extreme. We need to tell the client, if they're going to use 1,000 kilowatts of electricity in a year, or whatever that number is, what is the heat output? And if it's 2.5 megawatts of thermal power, that is a COP of 2.5. It's a very easy calculation. You only need 2 meters to do it. You know, our claims can be validated very easily. You know, but it's not just a commissioning. It will be over a 12-month period.
Right. Question from Gareth. By the looks of the presentation, your air source heat pump is a split unit, water source heat pump connected to a dry cooler. Is this how you cope with large delta T's, i.e. no requirement for a reverse cycle?
No, it's not water. On the air source heat pumps, we can use either glycol as the refrigerant medium in between the components, or indeed we can use propane. So we can then use hot gas from the compressors to defrost. But when we defrost, we send the hot gas back to the evaporators in a cycle, so that the output of the heat pump is not lowered during the defrost cycle.
Thanks, Ken. Question from Ella. How do the economics work for heat pumps on district heating in the UK, given we are expecting to connect mostly new efficient buildings with relatively low heat demands? This contrasts with, say, Denmark, where the vast majority of connected buildings are existing stock with higher heat demands and hence higher district heating operator revenues.
Yeah, do you know that's nearly into the politics of it, which I do know that one very appealing solution is an ambient loop system, where we will potentially take the source, get the loop up to say 25 degrees at very, very good COPs, and distribute that round with of course hardly any heat losses in the system, so that the individual heat pumps in the buildings or in the actual premises can deal with that. So I think the advancement in design philosophy that we're now seeing in the UK will come up with answers.
Great. Comment from Andrew. Thank you, Ken. A good solid performance. I agree with that. Comment from Chris. Government have said that they will release a consultation on shifting carbon levies from electricity to gas in 2022. So look out for it and put in a response. Very important for the transition to heat pumps, as Ken said.
Yeah, absolutely.
Yeah. Question from John. The recent government consultation on heat network zones envisages large-scale connection of existing properties to district heating. Given the traditional temperatures for building internals, do you really envisage all properties retaining existing gas boilers for bivalent operation?
I think there's a difference there between domestic and commercial.
Right.
I think commercial, the answer is probably yes. I think the route to decarbonisation, most commercial buildings will be a bivalent system. I doubt whether the district energy schemes will advance quick enough for our targets for 2050. I think the only answer at the moment is a heat pump, either on its own or combined with gas.
Thanks, Ken. Question from A. Toppin. Do we size thermal storage stroke buffer vessels to maximise run hours during lower tariff periods or to omit storage for peak demand? Understanding that it must be a trade-off, as increased storage would entail larger standing losses. What methods are applied to determine this? Well,
do you know the thermal stores that Solid Energy use are not for any other purpose than to stop cycling. What we don't want is on-off of our heat pumps. We don't want to have any more than 2 ons and 2 offs every hour. So our thinking is to protect the heat pump. The other aspects of thermal storage relating to the demand side, what does the building need? Or indeed, what would the national grid need? And the arguments around the sizing of the thermal store to deal with that, it's still really in its infancy. I've got a thermal store calculator which I can distribute as well.
I think that'd be useful, Ken. Yeah.
But that's an in-house tool, and it gives you really the minimum size of thermal store that Solid Energy wants, and I think other heat pump manufacturers want as well, to prevent any cycling of the unit. As regards though to the benefits of thermal stores, the bigger the thermal store, the better, as far as heat pump manufacturers are concerned. It is, people said, well, how big is too big? Well, too big is only when if you filled up the thermal store overnight and it didn't completely discharge the following day, then it's too big. But other than that, it's fine by the heat pump, because what we actually want is heat pumps to run for long periods of time. We do not want the quick blast of a combustion gas boiler. Those days of 15 minutes on, you can raise the temperature to 85. It's gone. It's got to be a much more gentle operating cycle.
A comment from Darren. Your statement about retrofit with existing fossil fuel systems makes more sense if we start to consider hydrogen as a fuel source for the future, which seems to be the case based on HyNet Northwest study.
Absolutely. I'm doing a scheme at the moment with LPG boilers and heat pump, with the intention that LPG will then be replaced by hydrogen in the future. So yeah, we can use that as another motivation for maintaining the gas boilers, with the hope that hydrogen will come along. And whereas I don't see hydrogen for a long time being in the pipes, the grid, I do see it being delivered to big sites.
Yeah, comment from Paul. Thanks. Need to go, but great slides. So, and then comment from Chris Dunham. Use decent techno-economic modelling software and you can find the optimal thermal store size considering losses and electricity prices. The Danish software Energy Pro is ideal for this. So there's a bit of help there.
Well, Energy Pro, there's another one now called HCSE. That's a great modelling tool for heat pumps as well. Again, what I'm giving is homemade calculators to get the design process moving.
Question from Montesino. What about the associated costs with proprietary software used by many manufacturers? That's regarding maintenance. This avoids many maintenance engineers being able to diagnose and fix an issue.
No.
Meaning there are costs to the client regarding call-outs and so on.
I'm with that. The guy who made that question, I understand it entirely. I can assure you that most large heat pumps, solid energy included, total open protocol, Siemens controls, any refrigeration engineer can clip onto the system, and all large heat pumps are connected to the internet anyway.
Yeah, and we've got interesting response to Rosella's question above. The answer to that question is if the HP cannot cope with a bigger delta T, you triple the flow rates on the primary if you have a third of the delta T. So just a comment about that. Breed. Thermal store calculators would be great. Bigger the better about buffer vessels. Comment from Siddiqui, there's evidence that more than 40 hours of storage in TES becomes redundant.
Yeah, I can believe that.
Comment from Darren, with regards to current LPG, the replacement is already in place with bio LPG. Great presentation, thanks. Thanks for the presentation, thank you. Any other comments? Thank you for the presentation. And I think that's it, Ken.